Okay, thank you very much for the introduction, and also for the opportunity to give this talk to you today. So, as was said, I'm going to talk about TROPOMI, but I'm also going to give some more introduction on the fields that we are working on, because I think this colloquium also has a broad audience today. So what I'm going to cover in this talk is first an introduction to KNMI and the group I'm working in. Then we'll be talking about the atmospheric composition and the global challenges that we are addressing in our field. Then I'll talk about TROPOMI and the measurements that we do, and I'll finish up with some examples of how the data of this instrument are being used at KNMI, but also, of course, elsewhere. So, as already said, I am from the Royal Netherlands Meteorological Institute, which is the Dutch National Weather Service. So KNMI is involved in the weather forecasting, but also in other activities around weather, climate, air quality, and seismic activity in the Netherlands. We have three large research and development groups that are more dedicated to science. And in addition to that, we have more operational tasks in running the meteorological instruments and doing the meteorological forecasts in the Netherlands. So when I was preparing this talk and I was thinking about how to do it, one of the first things that came to my mind is to compare the Netherlands, where I come from, with Canada, where you all are. And of course, there are some big differences. Of course, the Netherlands is quite a small country, which is about 240 times smaller than Canada. And the highest elevation in Canada is about 18 times higher than what we have. Although Canada is much larger, the population is actually only about 2 times larger than the Netherlands. So that means that our population density is quite high in the small country that we are. So that has implications also for the field that I'm working in. For example, on air quality, because larger population densities in general will give more of these kind of problems. And also related to climate, we face some unique challenges, because about 30% of the Netherlands is under the sea level, which means that that sea level rise due to climate change can have big consequences for our country. So the satellite department in KNMI is about 45 people, and we are working on the OMI and TROPOMI and GOM2, more the atmospheric composition missions. But also we have some of the leading scientists on wind from space, from spectrometers, and from the aerosols LiDAR instruments. And also a group focusing around aerosols, clouds, and radiation, for example, preparing the Earth Care mission and work on the Meteosat data. What's kind of unique is that we have a full chain approach, where we do missions from the start, more focusing on mission requirements. We have a lot going on development of algorithms and software, all the way to the scientific data products and operational data products. And our main funding sources for that work is the Netherlands Space Office, ESA, EUMETSAT, and the EU. And this link over there, you can find more information about what we do in our group. Now let's turn to the topic that I'm going to talk about today, which is the atmospheric composition. And this is a picture taken from the ISS, and I think this is very interesting to look at the atmosphere in this way, because as you can see by the laser pointer, also the atmosphere is really a very thin layer around the Earth. When you would shrink the Earth to the size of a basketball, the atmosphere is only a few millimeters thin. And that is the atmosphere that protects us from the harmful UV radiation. It's the atmosphere that provides us the livable climate, and it's the atmosphere that gives us the air to breathe. So that's really interesting to see that it's actually such a small layer around the Earth. When you look at the composition of the atmosphere, we see that it's mostly contains nitrogen and oxygen, then around 1% argon, and then there's this tiny fraction of 0.04%, which we call the trace gases. And these trace gases contain the greenhouse gases like CO2 and methane, the complete ozone layer, as well as the more reactive gases like the nitrogen oxides and etc. So it's this part that we mostly study, these trace gases. This actually a very small fraction of the atmosphere, but as you understand, a very important part of that of the atmospheric composition. Now, when you look at the atmosphere and see all the processes that are going on around atmospheric composition, you can see it's quite complex. At the surface of the Earth, there are all kinds of emissions. These can be natural emissions like desert dust or natural forest fires or volcanoes, but there's also a lot of anthropogenic man-made emissions, and these can either be new substances that we bring in the atmosphere, like for example the CFCs, or it can be an increase of concentration of gases that naturally are also in the atmosphere, like CO2 or methane. And these atmospheric emissions, they are quite important. They are really changing the atmosphere, leading to some big challenges. Now, when you emit a gas in the atmosphere, what happens to it depends very much on its atmospheric lifetime. And the atmospheric lifetime is determined by how reactive it is. For example, if you take the CFCs, which are depleting the ozone layer, these gases, they are not originally in the atmosphere. They have been made to serve as cooling agents, for example, in refrigerators or in air conditioners. And these do not react very well. So that means that they can be all the way transported all the way up to the stratosphere. And in the stratosphere, they can cause the depletion of the ozone layer. And some of these CFCs, they have atmospheric lifetimes up to half a decade, so really, really long time. Other species, like for example, NO2, that I'm going to talk about also a lot, is much more reactive. It reacts within a few hours in the atmosphere, so that means it cannot be transported over long distances, so it will be more regional than some of the other gases. So the man-made emissions, they cause global challenges regarding the ozone layer, air pollution, and climate change. And I'm going to introduce these now in the coming 3 slides. So let's start with the ozone layer. So the picture that you see here, this is the satellite data record. And what it shows is the concentration of ozone with the South Pole pointed towards you, and for each year it's the mean in the October month. And what happens over the South Pole during the winter is that there is this vortex which becomes very cold, and this vortex prevents mixing from the polar air to the lower latitudes. So it's kind of separated. It's like a separate amount of air. And once the light comes in the spring in the southern hemisphere, then you get this ozone depletion due to the CFCs. And as you can see in the early 80s, the ozone hole became rapidly bigger each year. And then after that, it seems to be more or less at the same level. But this is not because the amount of CFCs stopped at that point, but it's because at the levels, at the altitudes where the ozone is depleted, the concentrations are almost zero. So there's no ozone further to destroy. Of course, we have the CFCs regulated by now, which happened in halfway the 1980s. But because of these long lifetimes, it will take many years before the CFCs concentrations will go down and the ozone layer can recover. So the CFCs that currently are destroying our ozone layer this year, they may have been emitted like 10 or 20 years ago. So that's very important to take into account. Another challenge is, of course, air quality. And air quality is much more regional problem caused by aerosols, particles, or PM2.5, it's sometimes referred to, and ozone, which are both formed in the atmosphere by precursor gases, like, for example, SO2 and NO2. And as the amount of premature deaths due to air quality are estimated to be like 7 million globally every year. So it's a really big number. For example, if you compare it to the amount of COVID deaths in last year, that was, I think, estimated around 2 million. So air quality is really a big thing for our health. Not only for us as humans, but also it has an effect on the biosphere, including, for example, plants, and also affects the crop yield when ozone concentrations in at the surface become high. And here it's kind of interesting of this dual role about ozone, because I talked about ozone layer in the previous slide, which was the ozone layer in the stratosphere, which protect us from UV radiation. But ozone at the surface has another effect, because it's toxic for us as living as humans. But also here, of course, there have been regulations in place for a long time. For example, in the Netherlands and Europe, we have the European regulations around air quality. And also these are quite effective if you compare the pollution levels currently in the Netherlands with what it used to be when I grew up. Then today we are in a healthier world. And this we can also show, this is an old graph, which shows in the red line shows the amount of kilometers driven in the Netherlands. And then you see these two other lines, which is the emission of lead and the emission of NOx. And you see that in the beginning, the emissions, they kind of scaled with the amount of kilometers that were driven. But at a certain point, when regulations are come into place, first the lead emissions decrease, and then also the NOx emissions decrease, while still the amount of kilometers driven increases. So that's a sign that these regulations really are effective. But of course, they're not effective enough or strict enough, given the number of premature deaths that we still have. And of course, in certain countries, the air quality is much poorer than what's shown here. For example, if you think about about East Asia. Third one is climate change. I think all of you will be probably familiar with these kind of graphs showing the CO2 emissions even increasing in the atmosphere. This causes several effects. As I said in the beginning, 30% of my country is under sea level. So sea level is important. So this is a Dutch graph showing the sea level rise off the coast in the Netherlands over the from 1890 until present, and you see the steady increase, which is believed to enhance even further in the future. So this is probably the biggest challenge for us as humanity right now is climate change. So, as a working in the atmospheric composition field, science of scholars is driven by discoveries. We want to discover new things. We want to unravel how the atmosphere works and how the processes are ongoing in the atmosphere. But given these global challenges, there's also another part to our field, that is the policy making that we support. So once something has been discovered, like for example how CFCs destroy the ozone layer, there can be a decision by policymakers to put into place regulations on certain emissions. And these will be implemented, for example, in industries. And then we as scientists are also involved in the evaluation of what's going on. So we evaluate with our observations and models how the regulations, if they are effective or if more has to be done. And I think this is quite an important part of what we do in our field. So it's not only the discovery of where science plays a role, but also very much in this evaluation part. Now moving on to satellites, and in particular the TROPOMI instrument. So the TROPOMI instrument is in a way a much improved version of the OMI instrument. And the OMI instrument was launched in 2004 and still functioning after all these years. And the TROPOMI instrument was launched in 2017. Its mission duration is nominally 7 years, but we hope to, like OMI, to last much longer. And the instrument is doing up until now really, really good. So we really hope that we can extend the mission many times. The TROPOMI instrument was developed in the Netherlands together with ESA. And the mission, the Sentinel-5 Precursor mission, is part of the big Copernicus program in Europe, which consists of a whole range of satellites observing not only the atmosphere, but also land and ocean. With this, the S5 Precursor carries only the TROPOMI instrument. This is really targeting the atmospheric composition. So in the abstract that I put together for this talk today, I put in these two images, and I put them here again as teasers to show what can be done with an instrument like this in terms of mapping the global composition. But before going into this, I would like to talk some more about the principles of the measurements that we do. So TROPOMI is a spectrometer that measures in the shortwave part of the spectrum. So that means that the source, what we measure, is the solar light reflected by the Earth and in this atmosphere towards the satellite. That's our signal. So we measure on the on the day side of the orbit, and that's what we do when we are at the day side of the orbit. However, during at one point in the orbit per day, we also measure the sun directly. And what we usually use as our measurements is the radiance that comes from the Earth divided by the solar irradiance. And that's done for two reasons. First of all, it's kind of self-calibrating in that way. And secondly, there's a lot of spectral structures in the sun spectra that are in this way divided out. So you end up with the reflectivity of the Earth atmosphere, the Earth and the atmosphere, without all these spectral features of the sun. So that's the start of our measurements. The measurement principle is that we are a spectrometer, so we spectrally resolve the light. This is shown here schematically. If you have no absorbing gases, and if you have some concentration of NO2 and a high concentration of NO2, and you see when you have some NO2 in the field, you see all these lines, and these are the lines where NO2 specifically absorbs the light. So each gas has its own absorption spectrum, and we can use that to really recognize the gases like a barcode is used. When you increase the amount of NO2 in your spectrum, you see that these lines darken, and the measurement principle is that we compare our spectra with the known absorption cross-section of NO2, and then the deepness of the line, of the more blackening in the spectra, as you can see here, indicates higher concentrations. And this is how we analyze these spectra. And you will see in a couple of slides some more explanation on this. So we measure spectra, and we do that with a very sophisticated camera system. And at the heart of this system, there are two-dimensional detectors. And these two-dimensional detectors, they are used to record the spectra. On one axis, we put the spectral information, and on the other axis, we put the spatial information, so a cross-track. So it means that this area here on the Earth is imaged onto this detector, and one ground pixel here is imaged as a complete spectrum here and recorded as a spectrum here on the detector. And by using these two-dimensional detectors, we can actually record more than 400 of these spectrum at the same time. And we do that for about 1 second in flight time, and then we start the next one, the next 400 spectra to be recorded. And in this way, we cover the complete Earth with our measurements, because we are flying in a low Earth orbit. And it means that we do one orbit in about 1.5 hours, or we do about 15 orbits a day. And with this wide swath that we have with our instrument, we can cover the complete planet with measurements in just a single day. And to show you the real thing, this is the TROPOMI instrument when it was being integrated in the clean room in the Netherlands. Here at the back end, this is the optical part of the instrument. Here, this orange part is where the instrument looks towards Earth. So the orientation would be that Earth would be facing upward here. And this other part here in the front is where the light from the sun comes in. So you see that the instrument is about a meter cube approximately. Now, if you look at a functional diagram of the instrument, you see that you follow the light. You see that light comes from the Earth onto the telescope, and then we have in total 4 spectrometers: the UV, the UVIS, and the near, and the shortwave infrared. And the shortwave infrared is separate because it has to be at a different temperature than the other spectrometers. And each of these spectrometers is equipped with one of these 4 two-dimensional detectors. So we have in total 4 of these detectors that record our spectra. So we have these 2 ways of entering light, either from the Earth or from the solar port, which is then coupled into the telescope. And that's also a way where we can have other calibration sources like the white light source, LED sources, and the spectral line source to be coupled in when we would want to do special calibration measurements. So we have these 4 spectrometers. Again, you see them here, the UV, the UVIS, the NIR, and the SWIR. And then they are electronically split each into 2 bands. So in total, we have 8 bands. And as you can see, these these bands are spectrally chosen to cover certain species. The UV, it's mostly the ozone, and then the UVIS covers a wide range of of data products. In the near infrared, it's mostly aerosols and clouds that we're targeting. In the shortwave infrared, we have CO and methane. Now there's a whole lot of information on here, but what I'd like to point you at is the spatial resolution, which for most of our bands is 3.5 by 5.5 kilometers, which is really good compared to its predecessors. It's about 10 times better than the OMI instrument is. And you see that it varies a little bit in the shortwave infrared. The pixel size are a little bit bigger, and in the short UV they're also bigger because of the very low signals that we have to record there. But the number to keep in mind is like 3.5 by 5.5 kilometers is the spatial resolution. So what does it bring in terms of measurements? So this is 1 day of TROPOMI data put on the map. And from all these wavelengths that we have, we kind of created a false color RGB image. You see that we have quite a good resolution. I always get the questions what these light things are here. And this is what we call sun glint. So it's the reflection of the sun in the water, which we get every orbit on the western side of our field of view. So as I said, we record spectra. So it means that for each and every pixel that you see here on the screen, we have a complete spectrum for all of our spectrometers. So it means that we have for each pixel about 4,000 wavelengths recorded in these 4 spectrometers, which you can see now the radiant spectra on the screen for one of these pixels. And already here you can see the absorption spectra of or the absorption of gases. For example, this very deep one here. This is the oxygen A band in the near infrared, and here you can see the ozone absorption features in the UV. So we have about 1 scan line per second, and we measure about 440 spectra per scan line. We have 3,000 scan lines per orbit, and when you do the math, we record about 1 terabyte of level 1B data every day, and that's a really large data set that we're getting with this instrument, and it's something really that users are struggling with the large amount of data that we are producing. Now to go back to a single spectrum and to look a little bit more detail on how we get our data or how we derive the concentrations of gases from our spectra. This is one example of one spectrum What you see here in the middle is the black one is the measured one. This is in the visible, and the red one is the modeled spectrum. And this modeling of the spectrum, we use the trace gas absorption spectra for NO2, which have been measured in the lab. These are the green line here in the bottom, the light green one. And we combine that also with ozone, which is some importance also in this wavelength range. This is dark green line. And then we have on top here a spectrum that we also add to the fit, which explains the Raman scattering. So it's inelastic scattering. And together with additional fitting parameters, we can construct this red line, and you can see that it matches our observations really well with a low fitting residual. And this is kind of the procedure, the fitting that we do for each and every spectrum that we record. So we are currently producing a list of trace gases with the instrument. So it's ozone, NO2, CO, formaldehyde, methane, SO2. And we have aerosols and clouds properties that we also have. So these are the operational data products that you will find on the archives. We are currently, together with ESA, working on new data products. For example, BRO and also the vegetation fluorescence. So these will become online, hopefully in the next year or two, also on the archives. So when you think about data processing, and I talked about the data volume that we have, you can understand that this is really a big task. So we have 3 data streams coming from the instrument. So there's one that we call the near real-time data, which means that these data are available to users within 3 hours after we have measured them. We have what we call an offline stream, which is available after 14 days. And then once every couple of years, we do a reprocessing where we reprocess everything with the latest and greatest algorithms and calibration. We also do routine quality control, doing checks on the data, but also comparing them with other instruments, including ground-based instruments for the different species, including also, for example, the TCON, where your group is also very much involved in. And of course, all the data that we produce are free and open to any user. That I think is really great of this mission. Now, looking at some of the data that we are producing, and this is just some data I took for recent days from our internal data viewer. So this is off the coast of India and Pakistan, and this first image on the left-hand side, and it shows tropospheric NO2 coming out of cities and power plants. And what's very striking here is that you have these very long plumes that you will find in the data coming from these power plants. And this is what we see around the globe. And this, I think, is really new with TROPOMI, because we have now the spatial resolution to resolve this. With OMI, that was much harder to do. In the middle panel, you see SO2. In this case, it's from a natural source. So this is from the Etna volcano, which was quite active in late December of last year. You can see here some freshly produced SO2 from the volcano, but also this plume, which was actually SO2, which was produced a day earlier. And we were able to follow this plume around the globe for several days, all the way up to the Pacific Ocean. And then on the right-hand side, you see CO observations. This is over Central Africa, where you see these plumes, and these are emissions from fires that we where each plume is kind of its own forest fire there in the region. So these fires happen there every year around this time of the year. So these are daily or snapshots of data that we gather. Of course, you can also put them together in like a yearly average. In this case, I took NO2, and I think it's a great example. So NO2 is produced when you burn stuff, whether it's fossil fuel combustion, whether it's biomass burning. When you produce it, when you burn, you produce NO2. So it means that when there would be no humans on the planet, this complete image would be black, with maybe every now and then a natural forest fire occurring. But you can see it contains a lot of information on what we as humans do on this planet. You can see, of course, the hotspots of NO2 over East Asia, where of course a lot of people live, but also a lot of the factories are located. We see also overpopulated, densely populated regions like Northwestern Europe. We have very high NO2 concentrations, as well as in specific places over North America and the East Coast and West Coast. Also, we have these enhanced concentrations over Africa due to biomass burning, and also over South America. And when you look very closely, you can also see these kind of emissions that are on the oceans. And these are actually the shipping lanes. So these are the shipping lanes of the big container ships and the big tanker ships that go around our planet and leave these NO2 trails behind. So there's a lot of information here, as you can see, that we have due to this really good sensitivity of the instrument, but also the good spatial resolution of the instrument. Now, I would like to go over some examples of data from last year, from 2020. I kind of looked into 4 topics. So the exceptional ozone seasons that happened last year, some methane leaks that were found using TROPOMI, forest fires in Australia and North America, and I think the big thing, of course, was COVID last year and still is, and I will show examples on what the impact was on air quality and how we see it with TROPOMI. So let's start off with the ozone seasons in 2020, and I'm showing here on the left side TROPOMI data from 15 March of last year, where you can see a large area with low ozone over the northern latitudes, and the ozone depletion in the northern hemisphere is not as strong as in the southern hemisphere, and this is because this vortex over the northern hemisphere is much weaker than over the southern hemisphere, which has to do with the fact that there's more land mass on the northern hemisphere. Nevertheless, every now and then you get a year where you have a very strong vortex, which kind of favors the destruction of ozone. This is what happened also last year, but which gave quite low ozone for some time in the northern hemisphere as well. And this is, of course, due to this exceptional meteorological situation that happened this year. It's not something that happens every year, but as you can see, was quite severe last year. When we look at the ozone hole in the southern hemisphere. So this is October 25th. We see that the ozone hole was quite big and especially long-lasting over the South Pole this year. That's what you also can see here in the graph on the right, where you see in the dots. This is the area of the ozone hole for over the Antarctica, over the Antarctic, for this year, and the gray ranges give the ranges that were found since 2007. So you can see that it kind of started a little bit later, but it really continued much longer than we had in previous years. And then in the beginning of December, the polar vortex broke down and the low ozone was mixed with the higher ozone from the other parts. This also had an effect on the UV radiation at the surface. So this is the UV estimates from the satellite data. So you see that this red area here in the Southern Ocean, but also on in South America, had really much higher UV doses on this day. This is the 1st of December, and is comparable to what you normally would find in the tropics or the subtropics. And this is due to the very low ozone in this region. So the UV radiation at the surface becomes much higher than what is usual there in that part of the world. So exceptional ozone seasons last year. Then moving on to methane. And with the TROPOMI instrument, we have some unique methane observations with a very high, good spatial resolution, much better than we had before, but also a much better sensitivity. And already several methane leaks have been found with the instrument. For example, over Turkmenistan, but also over the US, where there was a blowout. And here I show an example over Algeria that happened in the beginning of last year. So to guide your eye where you are, so this is the Mediterranean, and this is kind of Northern Africa. So it's over the Saharan desert that we found this, but we also could follow for several days. And when you actually zoom into that region to see what's actually there, you find that there is quite some industry related to the production of natural gas in this region, and that's where this leak seems to originate from. So it's very important to find these leaks and also to report them so that they can be stopped, because these emissions can be quite big and have an impact on the amount of greenhouse gases in the atmosphere, and therefore are important for climate. And we have several people looking into that, groups looking into that, also from oil and gas companies, because they also want to know about these leaks. Also last year we had some really big biomass burning events. First in the beginning of the year from Australia, and later in the year over North America. And here in the top I show the aerosol index. So this is a signal coming from the soot and the smoke particles that are produced, and these soot particles they were all over the southern hemisphere in the beginning of the year. You see here very big aerosol cloud, but also here you see traces of this cloud as the air moves towards South America and then towards Africa. So this was really a big event, of course, a tragedy for many people living in Australia, but also had big implications for the atmospheric composition of the southern hemisphere. Then in the bottom plot, you see CO on the 14th of September. You see that a very, very big plume coming from the North American West Coast fires, going the way over Canada, and causing air quality problems for a large part of the North American continent. So really big things to follow, and also to keep in mind that these might be occurring more often due to climate change. With TROPOMI, we can also do more quantitative work on these kind of emissions when we combine some of our data products, because here I show CO and aerosols, but we also have NO2 observations, formaldehyde observations, which are quite prominent in these kind of situations. And the plot here on the right-hand side shows an analysis where we combine CO and NO2 for different fires over Africa, which are the blue signals. The green ones are from South America, and then the reddish ones, they are from boreal fires. And you can see that there is quite a difference in the NOx, the NO2 to CO ratio for these fires. And this information we use to further improve the models and the emissions going into these models. So now going into the COVID part, which of course had a big impact on air quality because of the lockdowns in the different places, starting in February and March over China. Here on the left side, showing the 2019 averages for this period. And then the 2021s, you can, from the eye, immediately see the big difference in NO2 due to the lockdowns, the reduction in traffic, but also the reduction in industry and power generation in China. And we could follow this around the globe. So this is India, again comparing 2019 and 2020. And you can see that, for example, the city of Delhi here, which is very high in 2019, almost disappeared due to the lockdowns. But on the other hand, you have these power plants here on the more on the east side of China, of India, which kind of were on the same level as the previous year, showing that while probably a lot of activities like the traffic stopped, but power generation itself was more or less at the same level in India. Also over Europe, we have similar kind of numbers, where for the major cities in March and April, we estimate a reduction in NO2, mostly due to reduction in traffic of about 50% for the major cities like Paris, Madrid, Rome, and Milano. Also looked into North America. This is a very quick and dirty analysis that I did this afternoon, just taking the months May to September 2020 and subtracting the May-September 2019. What you see is in these major cities, for example, here on the US East Coast, strong reductions in NO2 as we have seen elsewhere. But we also see some other things, like for example here on in the west, we see some red spots, and these are actually related to the much bigger fire season this year compared to the previous years. When you look, for example, here over the urban areas of San Francisco, we again see a strong decrease in NO2 due to the COVID measures. Well, we also compared the data from our satellite with what we've seen on ground. So here on top, you see TROPOMI data in black 2019 and in red 2020. This is for Milano, Madrid, and Paris. And in the bottom, you see the in situ observations, so at street level for these three cities. When you compare the numbers, you see that it's very comparable with what we find from the satellite, with what we find from the ground-based data. And that's really encouraging and good to see that this compares well. Now, these were all kind of relatively simple comparisons, and a lot of them have been shown in all kind of media and done by many researchers around the globe. But these also have their drawbacks, because there's also meteorology in between. So comparing concentrations is not the same as comparing emissions. So for that, you have to do more thorough analysis. And here I'm showing some results from our group, where we did an inverse modeling of the, so we derived the emissions from the concentration data over China. And we compare the 2019 and 2020 period. So what we see here for urban areas over China, we see in 2020 this really big dip, and then towards March we see that it's getting at the previous levels. And also when we look at the power plants regions, so this is an area that is really dominated by emissions from power plants, we see similar kind of structures here. And I think this is really good, because this analysis really takes out the effect of meteorology and looks at the emissions directly. This is a very important thing to do. And it's maybe also a bit of a drawback of giving all your data free and open, is that a lot of people start comparing things without having the knowledge of an atmospheric scientist, and forgetting about meteorology and coming to wrong conclusions. And I think it's very important to, before these things are published, to really make this thorough analysis of the data, to really say something about the emissions, and having this meteorology out of the way. So that kind of brings me to the end of my presentation. So just to summarize some of the important points. So TROPOMI is the first of the European Sentinel program looking at the atmospheric composition. There's much more to come in the coming years. We will first have the Sentinel 4 and 5 instruments. Sentinel 5 is like a follow-on of TROPOMI, and Sentinel 4 is geostationary over Europe. But also recently the CO2M mission was acknowledged to and will go ahead. That means that we will have CO2 and methane, but also NO2 observations with a really high spatial resolution coming somewhere around 2026. TROPOMI, it provides daily global coverage with a high spatial resolution, really, I think, setting new standards for these kind of observations. We can use the data operationally for all kind of applications, but also, of course, for science, for exploring different things in the atmosphere and trying to address the global challenges that I talked about. Well, all of our data are open, and I always encourage people to contact the algorithm leads if you want to have more knowledge about the data, and if you want to work with us on specific parts of the data as we produce it. And finally, I have a slide with where you can find more information, where you can find the data, but also where you can find documentation on the data products. 2020 is going to be an important year for us. 2021 is going to be an important year for us because we will moving towards new algorithms and processors probably in April. And that's of course also very important for data users to follow. And we also hope to start reprocessing all of our data and bring out new data sets by the end of the year. So please keep an eye on what we post on that on these websites to ensure that you know what the data is that we are producing and to understand the algorithms. And with that, I would like to thank you for your attention, and I'm looking forward to your questions.